Suppose you have an electrical potential, V of x, and you want to find the behavior of an electron subject to that potential. That's described by the time-independent Schrödinger equation, which we write as minus psi double prime plus V psi is equal to E psi. Here, psi is the wave function of the particle, V is the potential, and E is the energy. And the goal is to find the wave function and the energy simultaneously. To make this problem well posed, we have to add a couple of boundary conditions. So we'll just set this function equal to 0 at both ends of some interval. That corresponds to an infinitely high potential. This problem has an abstract form a times psi is equal to lambda psi. Here a is a linear operator, a differential operator, and lambda we could call an eigenvalue. In Chebfun, we represent a as a Chebop, and we use eigs to find the wave function and the eigenvalue. Now we'll solve an instance of the Schrödinger problem in Chebfun. I'm going to solve this problem on the domain minus 5 to 5. So here's a potential function defined on that domain. It's what we call a double well potential. It has 2 drops on it. And I made it asymmetrical just to keep it more interesting. So now let's create the Chebop, the operator, based on that potential. So here's the differential equation part of it. And then the other side, the E times psi, we don't have to specify. That's part of the eigenvalue problem itself. So we do give the domain, and then we tell it that we want the eigenfunctions to be 0 at the left and at the right. And with that, we can solve for the wave functions and energies using eigs. So let's get the first 30 of smallest real part. And there they are. So the energies themselves are there. And we can plot the wave functions themselves. I'm going to scale them just to make them more visible. So there are the first 3 eigenfunctions. You can see which one, the blue one must be the lowest energy, and then the green, and then the red. But they're all more or less confined to that left well, because that one's lower than the other. But if the energy gets high enough, eventually, you see that there are eigenfunctions associated with the other well. So here's a few more. And then you see that the way the energies work out is that you kind of bop back and forth between those 2 wells. But you still have an exponential decay inside the tall part of the potential. Eventually, though, the energies get large enough that the electrons can overcome that, and we get a global wave function. That's the quantum mechanical tunneling effect.